So in this tutorial we're going to look at how to draw and how to read histograms. So let's have a look at an example that we produced in the previous video. So here's a histogram of 100 cats, the weight in pounds of 100 cats. And so we took the raw data and we drew up this histogram which shows frequency on the y-axis and the weight categories on the x-axis, or the vertical and horizontal axes here. So let's just read the histogram, make sure we understand how to read this kind of histogram. So we've got between 2 and 4 pounds, we've got just one cat. Between 4 and 6 pounds, we've got 4 cats here. Between 6 and 8 pounds, we've got 18 cats. And our largest category here, between 8 and 10 pounds, we've got 60 cats that weigh between 8 and 10 pounds. 11 pounds, 2 pounds, 11 cats, 2 cats, 2 cats, and then just at the edges here, as we would expect, it tails away. So just one cat between 16 and 18, and one that weighs between 18 and 20. So those are our 100 cats, and that's our histogram. And we would say this is normally distributed because although the central category here, the central class, is rather higher than expected, everything else pretty much is lining up with the normal distribution bell curve. Okay, so what I'm going to do now is draw another set of axes and redraw this with the idea that we're given slightly different data to start with. So grouped frequency data is going to be slightly different, and it's going to be different in this respect. They're going to give us unequal class intervals. So let's say we're given data only between 2 and 6 pounds. We're told there are 5 cats between 2 and 6 pounds. We'll keep these classes the same, so 6 to 8, 8 to 10, 10 to 12 we'll keep the same, but again we're going to join together and say these intervals. So we're going to say there's just a class interval that we're told that there are 6 cats that weigh between 12 and 20 pounds. So what we've got here now is bins that are not of equal size, so bins or class intervals that are not of equal width. Now this gives us a problem that we can illustrate if we just draw up our first class intervals that aren't changed. So we've got this frequency here, this frequency here, and this frequency here. Our problem comes when we draw these outside categories, because if we just add together 1 and 4 to make 5, and so draw this up to here, and add this 2, 2 and 2 again, so we've got 6 cats here, and draw it up to make 6, then when I overlay my normal distribution curve, it looks like the data isn't normally distributed, and that's because we would expect the data to drop off at the tails here. And if it's not dropping off, we call this fat-tailed behavior. If it's not dropping off, we might suspect that we haven't got normally distributed data, and that wouldn't be correct. So there's a problem here, and you can see the problem particularly in with these two areas here. With our original histogram, where the intervals were equal, we had a tiny area here which is roughly half, just over half the area here, and that's as it should be shown. But here the area has become almost twice this area here, and that's why the shape now isn't showing a normal distribution. So we've got to alter these bars, and we can alter all of these bars, bring them down and change the areas. But what I'm going to do in fact is let's just erase this one first of all. What I'm going to do is I'm going to number the axes in a different way. And the reason I'm going to do that is because very often when we look at an unequal class interval histogram, we don't get these high numbers, and that's because we're no longer able to read frequency off from the y-axis. Now I'll show you what I mean by let's erase these two categories here and just start with these intervals here which are unchanged. Now The concept here is to study the area now then occupied by these rectangles and not the height. So we want the area of this central bar to equal 60, not the height to equal 60. So again, if I record what we want, so we want the area to equal 60, not the height, then how do we calculate the area of a rectangle? The area of a rectangle is calculated by width times height. If the width is 10 minus 8, 2, and the height must be 30, because 2 times 30 will give us 60. So the area now is the frequency, the height has to be 30. And instead of height, what we're going to call this axis now, and it's the giveaway for this kind of histogram and shows you how to read it, we're going to call the height now of each of the bars frequency density. So it's the density, if you like, of the area here. It's how much this is filled with little balls or particles of sand. And that's why we call it frequency density. But all frequency density means, so frequency density, all it means is that we're measuring now the height of the bar and multiplying it by the width, which is given by the class interval, in this case the weight in pounds. Okay, so we've calculated this bar now correctly. We've got 30 times 2, which is 60. That defines the values on the x-axis, which we can number up now. So 5 intervals of 5 on the x-axis. Okay. Now let's look at this bar here. Now this should already be correctly drawn because it's in the same proportion as the central one that we defined. So let's just check that. So 2 times, well, we've got 9 here, so this height now is at 9. So 2 times 9 gives us our frequency of 18. So the area of this bar is 18, and that gives us our frequency. 10 to 12 category, well, the bar is now drawn at 5.5, so 5.5 times this 2 gives us an area of 11. So where we have to readjust our chart is only now on the edges. Let's start with this one here. So between 2 and 6, well, our width then is 4 now. So we've got a width of 4, and we've got to get an area of 5 because our frequency is 5. So 4, let's just do a little calculation. I'll do it in a different colour so we don't get confused. Let's do it, in fact, let's do it up here. So 4 times the height, so 4 times the height, so we don't know what the height is, so let's just call that h, is going to give us now our frequency of 5, which is the area of the rectangle. So 4 times the height equals 5, so the height must be what? 4 divide both sides by 4, and we'll get 5 divided by 4. Well, 4 goes into 5 once, and then we've got a remainder of 1, so it's 1/4. So 5 divided by 4 is 1.25. So what that means is that our height, the height of our bar, to get an area of 5 has to be 1.25. Well, if this is 5, so the frequency density is 5, then half of this must be 2.5, and half of 2.5, so here, must be 1.25, so 1.25 on our scale here. So now we can draw up our bar to this point here, and we've got an area now which is proportional with the other areas. Okay, so let's do this bar here on the right hand side of the graph, and again we want to make the area proportional, So we're going to calculate once again the height. We want the frequency to equal 6, so 6. So it's going to be very short, a very short height, so the height is going to be very low because we've got such a lot of width. Okay, so let's calculate exactly what the height has got to be. So the width now is 20 minus 12, which is 8. So 8 times our height. Let's call our height this time I. So 8 times our height is going to equal 6. So our height here, our second value here, has got to be 6 divided by 8, which gives us 3/4 or 0.75. Well, that's a little less than half the height of this bar here. So let's now draw this very close to the axis, so about here, and then draw up our bar. Okay, now finally we can superimpose our normal distribution curve again, so let's just draw that over the top, and we can see now that the areas are proportional, and we've shown what we wanted to show, which is that our data is normally distributed, apart from maybe the central tendency, which is a little higher than expected. Okay, so that's how to draw a histogram. Let's now look at another example where we're going to draw up a histogram, but practice reading a histogram and calculating the frequency from a given histogram that's based on unequal class intervals. So what I want to do now is imagine a different situation. Let's imagine now an apple orchard with a number of trees with different numbers of apples. Let's just think about how we would draw that. So what I want to look at on the x-axis, on the horizontal axis, is, let's just draw up a central bar like that, is percentage now of apples. Okay, so I'm going to draw, let's draw up to here, so this will be 100%. Okay, and so here would be a 50%. 50, 60, 70, 80, 90, 100. Okay, so that's correct. So we've got 0% of apples here, 50% here, and 100% here. And let's say percentage of apples that are eatable. Let's say good. So our central tendency here is apples that, so percentage of apples, trees that have a percentage of apples that are eatable, and we've got sort of, around 50% is the average. Okay, so most trees have about 50%. Let's draw up a couple more bars. Okay, so let's try this one. This. And a large category here. Okay, so here we've got percentage of apples. On the y-axis, I'm now going to draw frequency density. So let's just call this FD. And very often you get fractions on a frequency density because you're multiplying by the number here. So we're going to use some very low values here. Let's go up in decimals then. So 0.2 would be to here. So in that case, this would be 1. And if I go up another 5, this would be 2. So the highest bar is going to be recorded at 2.4. Okay, so there's a typical histogram that shows us frequency density on the y-axis and values on the x-axis, and to get the frequency of apples, so the problem is, let's say we need to calculate how many trees in our apple orchard then altogether. Okay, so that's our problem. To get that, we need to calculate the frequency in each of these class intervals. So the first frequency we can calculate by multiplying the width times the height. So again, let's use a different colour for our calculations. So first of all, we've got our frequency density, which is 0.2. So let's call this A, B, C and D. So for A, 0.2 times, so that's the height, times the width. Well, let's just check the width. Okay, the width of this bar then is, well, we're numbering up now in tens. So in fact, let's just put these on here. So that's 10, 20, 30, 40, 50, 60, and then we've got an interval between 60 and 100. So here we've got a width of 10, so it's 0.2 times, let's just keep to that colour there, so I'll just erase that for a minute. Okay, so we've got A is 0.2 times the width, which is 10, which gives us 2 trees. So our frequency for this class interval here must be 2. Okay, let's have a look at column B. So column B, the width is 40 minus 20, which is 20. And so 20, let's record that there, so that's the width. And the height now, we read off from our frequency density axis, so it's 1.2. 1.2 times 20, so that's 2.4 times 10, giving us frequency of 24. So there are 24 trees that have between 20 and 40% of apples that are eatable. Okay, now let's look at this category here. You can just make it clear that it's between 40 and 60 here. So class of trees that have 40 to 60% apples that are good, that are eatable. So our height is 2.4 times our width, which is 20 again. So 2.4 times 20 equals 4.8 times 10, which is 48. Finally, our last frequency is 40. So 40 is the width, and the frequency density, which is the height, is 0.6 then. 0.6. So we've got, well, again, if you want to just calculate something like this very quickly, it's a good idea to go over to one side, make a little check. So we've got 6 times 40, you can do this mentally, but 6 times 40, 6 times 0, 4 times 6, 24, and we've got 1 decimal point, so the answer is 24. Okay, so between 60 and 100%, trees that have between 60 and 100% good apples, we've got 24 of those trees. Now, as a check, we would want to total these up if we knew how many there were in the orchard, but in this case, that's exactly what we were asked to calculate. So I'm just going to make sure we've got our data lined up here so we can add it straight down. Okay, so that should be 2. So we've got 2 add 4 is 6, add 8 is 14, add 4 is 18. Make a little note of that, but let's calculate up again. 4, 12, 16, 18. So if we note down the 8, carry the 1 or the 10, 2 add 4 is 6, 8, 9. So going up again, 1, 3, 7, 9. So 9 is correct. So we've got 98 trees in our orchard. Lastly, what about adding this normal distribution curve over the top, superimposing it, putting it over the top of a histogram like this? Well, it's not strictly speaking necessary, but when you've got unequal class intervals, it becomes a slightly different proposition. So in part 2, I'm just going to consider that idea. Okay, so if I want to draw a distribution curve, a normal distribution over the top to see whether this is normally distributed, then what I'm going to have to think about is, well, where is the peak going to be of my distribution curve, for example? Is it going to be in the middle here, or is it going to be over here? And then where will it tail off? And roughly what shape is it going to be? Now, to superimpose a normal distribution curve effectively, and so that I can use it to draw some pretty reliable conclusions about whether this is normally distributed or not, one thing I like to do is think about the number of bins that there would be in terms of, well, say a Galton board where the balls are dropping into bins. Now, this time we haven't got equal class intervals. So we've got a problem. We haven't got an equal number of bins. So what I need to do first of all, I think, is to draw over the top where the bins would be for my normal distribution curve. So I'm going to start like that, drawing up some lines so you can see, first of all, how many bins we would need to superimpose. Now, you can have two ideas here. You can say, well, the data starts here and finishes here. So if I count this up, I've got 4, 5, and another 4. That's 9 bins. We're going to start with the idea of 9 bins. But you could also say, well, there are 10 bins. Now, it looks as though there's no data in here. So in other words, there are no trees, it seems, that have less than 10% eatable apples in them. So there are no trees with 5%, for example. But that doesn't mean that the normal distribution curve won't start in this very small category here, just because our data doesn't seem to have fallen into that class interval. Nevertheless, let's assume to start with that the data does actually start here and finishes here. So let's start with the idea of 9 bins. Now, if I have 9 bins, then my peak is going to fall in this interval here. In other words, we've got one category, if you like, here, which is the central one. Okay, so 9 bins, you've got 4, 4 and 1 central bin. So I can draw up then from the top here a normal distribution curve that peaks here, that goes over the top here and then comes down and out to the sides, tailing off to very low values at the ends here. So let's have a go at that. Now I've prepared one that I drew earlier because it's actually quite a difficult thing to draw, but just to show you, it would look something like this. So there we go, nice, smooth, normal distribution based on 9 bins. Okay, so these 9 bins are showing me the shape of the, if you like, the outside edges of my curve. If I fill the bins now, the first bin I would fill up to this point here, and I'm just using a transparent colour here so you can see how it compares to the actual data underneath. So let's now fill up the class interval that goes between 20 and 40. So now there are 2 bins between 20 and 40, so I'm going to fill up to here and fill up to here. So we can immediately see that the actual data is showing a much larger area. Remember, it's area that we're looking for, not height. So it's showing a much larger area than the normal distribution curve. So these 2 bins here are not filling up nearly as much space. In fact, you've got all this green space left over. So that's interesting. So at the moment, this isn't showing that the data is normally distributed. Let's have a look at this central category here. So from 40 to 60. Well, one of the bins is going to go up to about here, and the other one is going to go right up to the top here. So let's just draw those in. Again, there's a little bit left over, so the normal data is a bit larger. The area of the apple tree data is larger than the normally distributed data. So again, we seem to have a bit of an excess on the left-hand side of our curve, if you like. Now let's consider the 60 to 100% category, class interval. And here we're going to have to draw 4 bins at different heights. So we're going to have 1 bin here, 1 bin at this height here, another bin at this height here, and then this little bin at the end. So let's draw those over the top at first, and then let's compare. Okay, so we have something like this, where you can see this area here now is actually larger. So we've got this area that's beyond the diagram. It's actually larger than the green left over. So what we've got is the data all shifted over really to one side. And what I want to do with my normal distribution curve, to try and make it match a little bit better, just to see if we can show that it's normally distributed, I really would like to move this curve over to the left. Okay, so before concluding that this isn't normally distributed data, let's now erase this line and start again. And I think you can see from that little experiment that 10 bins is actually going to give us a much better fit. So if we're going to assume we've got 10 bins rather than 9, we're going to start our curve from over here. We're going to go up to here, and again I've prepared a curve that I've drawn earlier because it's actually quite a difficult thing to draw, and I'm going to superimpose a 10 bin normal distribution curve now over the top. So that's certainly moved it a little bit to the left. Now when I draw up the histogram, you can see, I hope, that the areas now are roughly matching. Now they're going to be a different shape, but remember we're not looking at the height, we're not looking at the width, certainly we're not looking at the height, we're looking at the total area. So it doesn't matter that these are awkward shapes that are not following this curve. What matters is that the area is going to be equivalent. Well, here you can see that the histogram underneath is made up of 2 bins now, but if you added those together, those 2 areas would equal roughly, or maybe exactly, the area of the real data between 10 and 20%. If we look at the 20% to 40% class interval, we've got something very similar. We've not got the same shape, the heights here are very different, but if we imagine cutting this piece off here and fitting it into here, we can see that the areas in fact are almost exactly the same. Now there's a little bit of excess in the 40 to 60% class interval, so we could say this is not quite as high as we would expect. Nevertheless, it's not far off. And here again we want to imagine cutting this shape off here to see whether it would fit into here, and you'd have to maybe cut these in two, but I think you would see if you took those parts there and fitted them in here, again it's a pretty close, almost exact fit, so the areas are equivalent. So let's just remove the histogram and have a look at it. Despite then this very jagged appearance that we get with a histogram with unequal class intervals, if we look at the area very carefully, I think we can say we can see that it is in fact normally distributed. But it was very important to get this curve correctly drawn. So finally, what I want to do is just show you how it was that I planned drawing this curve, what it was I used to get the classic bell curve shape that I could then superimpose over the data. And the idea here was to use Pascal's triangle. So Pascal's triangle we may have come across before, but it's a very useful tool for drawing normal distribution curves. And the numbers in Pascal's triangle are what I've used here to get the height of my bins, and then once I've got the height, once I've plotted the heights on my diagram, I then draw those points together to get my normal distribution curve. Now here I had 10 bins, and so I wanted to get data for 10 bins. I was using the 10th row of Pascal's triangle. So what is Pascal's triangle? Well, we start by putting a 1 at the top, but imagining a couple of zeros either side. Now if I add this 0 to 1, I will get 1 again, so I write 1 underneath. If I add this 1 to this 0, I get 1 again, so I write 1 underneath. I've now written 2 rows of Pascal's triangle. Now I've got a 1 and a 1, and a 1 and a 0. Again, this invisible 0 on either side. So 0 add 1 gives me the 1 again. And after a while I'll stop talking about the zeros because you'll see the 1s are always on the outside. Now in the middle I've got 1 add 1, so 2, and 1 add 0 gives me 1. And you can see now all we're doing is adding the numbers above, so we can go actually very quickly. And in exam or test conditions, quickly drawing out Pascal's triangle can be a very quick process and can be very helpful. So 1 add 2 now is 3. I've got another 3 here, and then I've got a 1. So that's the 4th row. 1, 4. Now I've got a 6 in the middle, a 4, and a 1. Now this is beginning to look like a curve, like this bell curve. You've got a peak in the middle. You've got these 2 smaller numbers either side. So that's as the curve goes down, and then you've got the 1s at the end. Now, that's the 5th row. Let's look at the 6th row. 1, 5 then, 10, 10, 5, 1. And then we've got in fact, that's the 5th row, that's the 6th row, this is the 7th row. So now we've got 15. We have a middle value of 20, and then 15 either side. Now we've got the 8th row then. So we've got 1, 7, 21, 35, 2 35s in the middle. And then the curve goes down again. That's the 8th row. The 9th row. Looks like this. Now, let's just pause at this point. Obviously, this could go on forever, but I'm looking at the number of bins. Remember with the first example that I tried 9 bins. Well, we've got 1, 2, 3, 4, 1, 2, 3, 4, and 1 in the middle. Here's the row where we have, so it's the 9th row where I get 9 bins. And I used these numbers to start with to draw my first normal distribution curve that I attempted to superimpose over the data. That didn't work, so then I moved to my 10th row, and that goes like this. So 1, 9, we have 36 here. Okay, now we've got 28, add 36, so we have 64. Do we? Is that right? No, wait a minute, that's not 36. that's 56. So did I think I drew that incorrectly. So it's this one. 21 add 35 is 56. So we've got 56. So 56 add 28, and we've got 84. That's a more familiar number. Okay. After a while, you get used to the numbers. So now we've got 126, and in fact we've got 126 twice. Then we've got 84, 36, 9 and 1, and that completes the 10th row of Pascal's triangle. Well, how did that then get used to draw this normal distribution curve here? Well, let's just take our numbers and look at this scale. We want our curve to get as high as 126. So what I've done simply is use these ticks on the y-axis, but instead of using this scale here, I've just changed this number here to 0.6. This is in fact the 13th tick, so I'm going to call that 130. So here's 126 here and here on top of these bins either side of the center. Okay, so that's dealt with the highest value here. Now let's just make that a little clearer. Okay, we'll come back to that maybe. So now if I consider 84, well, that's going to be on top of this bin here. Maybe if I just mark where my bins are, actually, that would be a bit easier to deal with. There we go. So for 84, I'm going to be looking at this bin here from 30 to 40. So 84, well, that's going to be, if this is going to be 100, then this is going to be 50. So my 84 value is going to be about here. So that looks about right. That's intercepts with the curve, and that's right over these two bins here. Let's just mark on these 126. So the 126 is that right then? 120. Maybe I needed to draw that a little bit higher, but those are above those two bins there. Now I've got, so let's say we've done those. Now I've got 36. So that applies to this bin here between 20 and 30. So this is 30, this is 40, 36 is about here. So again, that's how we got that point on our normal distribution curve and that point there. Okay, finally we've got the 9 and the 1. Okay, so above this bin here, we're going to say that's 9. Okay, and above this bin here, and then finally the 1s, that will be here and here. And so once you've drawn these points using these values taken from Pascal's triangle, once you've plotted them on your graph, you can then join them up very carefully to create the bell curve shape. Erase, if you like, the, whoops, where are we? There we are. Erase your workings here, and that's a good way of superimposing a normal distribution curve over your diagram. Okay.